All right, I started recording. So I think last class we stopped here at pointer prefetching. Uh, all right, before we jump into this, does anyone have any questions about material so far? About anything else, projects, assignments, etc. Does anyone want to ask? Discuss something in the class?
So you said we could write the essay as a group?
Sure.
It would just have to be with a certain amount of detail commensurate to the number of people.
Yes.
Got it.
I want to, if you could provide write-ups by next Monday as to what you're trying to do. I'll provide feedback, by within a day or two, about what I think about your proposal, right? So if it needs more work commensurate to the number of people, maybe I'll provide some hints as to what directions you could look in, or just if I'm clueless about that thing, I'll just say, okay, maybe more is needed, and then you could figure it out or whatever. Yeah. All right. Any other questions? Anything else? We can also do this at the end of class, in case you think of something.
Do you want to just email that to you?
Sorry?
Should we just email that to you?
If it's easier for me to keep track of things on GitHub, then I just have a set of links, and then I just go look at them. Assuming you already have a project repository, put it in the project repository, and send me an email saying that you've updated it.
Sounds good.
Yeah. All right. Okay, so we'll start with pointer prefetching because somebody asked me to start here last class. The idea with pointer prefetching is we're trying to optimize data structures that are pointer based, right? So if you're looking at an array where data is consecutively laid out, we saw how we can deal with that kind of stuff last class. And then there's the other kind of data structures where they're made out of a linked list of nodes, or a tree of nodes, or graph of nodes, or whatever. And the kind of the way you traverse these things is you load one node, you use a pointer inside that node to access the next one. Now the issue with that is you can't really tell where a given node is. You can't really tell where a given node is going to be until you where the next node is going to be until you access a certain node, because it's a pointer-based access, right? So it seems like you have a strided access pattern, but then the actual memory layout can be anywhere. So one way that immediately comes to mind as to how you can deal with this is the fact that pointers inside a data structure tend to look different, right? Like it's very rare that you have numbers that are that large. I mean, there's the case, there's the really bad case here where you're doing scientific computation or something of that sort, and you're dealing with really large floating point numbers. In that case, everything looks like pointer, and this kind of a predictor will go haywire. But then, as we established earlier, being being wrong is not a problem. The prefetcher may just cause a performance loss. The hardware make sure that you never actually end up operating with the wrong data, right? Because you have checks that do speculative, that verify that your speculative execution is correct, and this is all speculative execution. So if you were to look at some data that looks like this, and you walk through this whole thing, you have those two numbers there that maybe pointers. They're pretty large, and they have some kind of regularity to them. So one way of prefetching a pointer-based data structure is you load one node. While you're loading that node, you look through the node, you look through the piece of data that you're fetching in and say, hey, this particular chunk of data seems to look like a address. Let me go ahead and prefetch this. Now, you can also look at into the TLB and say, hey, is this a valid address at all? Am I fetching some random nonsense, or is this illegal? In which case you don't do it. If it's not mapped in the TLB, you don't prefetch, right? You don't go walk the page table. So this, in some sense, allows you to walk the tree or another pointer-based data structure, and it kind of works. The reason why it doesn't work that well is you have pretty limited look ahead, right? Like you have to load, if you had a stride prefetcher, you'd look at, X, and then by the time you came to access X plus one, you've kind of got X plus one loaded because you're going further ahead, right? So you have that kind of an access pattern. If blue is, access, and the access latency is for some node that you're fetching. Whereas in the binary prefetcher, they're kind of serialized. When you access A, you then get the pointer for B, and then you go and initiate the fetch, and you still you don't save any. You save the compute time that you would operate on A, right? Like if your compute time neatly overlaps with access latency, then you've won. If not, you've saved a little bit, but not much. This kind of a prefetcher is actually really cheap to implement, because all you're doing is kind of comparing with 60, whatever the address size is, right? 32-bit or 64-bit. If you're taking the data you loaded, chunking that up into 32 or 64-bit values, and then checking those values against a TLB. So it's not a lot of hardware to implement. So yeah, it's a little, oh, sorry. Yeah. So it's easy to implement. I guess then the question becomes, can we do better? What else can you exploit about a linked data structure that allows you to figure out where to go? How would you design a prefetcher for a linked data structure? Most reuse, or data reuse essentially comes from two types of locality. What are the two types of locality?
Spatial and temporal.
Yes, they're spatial and temporal locality. Now, can you use one of either, any one of those to prefetch, to do something to optimize prefetch for pointer-based data structures? As for the whole class thing, but not just much. What do you guys think? Which one of these would you comes to mind, what can you do with it? Spatial and temporal locality.
I mean, I think temporal is the one you need to use, because if it's a linked list, then each node you go to will always be in the same order, whereas locality doesn't really help you because it could be going to anywhere.
Yes. So how? Okay, that's correct. Observation. What will you do? What would you do with that? How would you design a structure that allows you to make use of temporal locality? We've seen a similar structure before, right? So based on what you know from in order or spatially, aligned arrays and things like that. What can you build for a pointer-based structure? Let's break the question down. What do you need to store? If we were to think of this, in like a software implementation, what would you store? No one? No one has any ideas?
You would store like the ID of the node, and then you would store like the almost like a stack of like when they were accessed to see which ones are accessed together, like that maintains the order.
Okay. Could you do a different data structure, perhaps? That the storage, could you do it in a different data structure, perhaps? What? Okay, maybe I'll just show you what I mean. So, the most efficient way of building a temporal correlation table is to use a map, right? Like this is a map. You have a key, and it shows you where to go, where you went the last few times. So the way this, a correlation, like this, we're calling this a temporal correlation table. The way this table would operate is, you'd say A, right? You go to A, and then next after A, you traverse to B. So you come in here and you write down, index into A, wherever that goes, hash it, goes in somewhere. You insert the node that you're on, A, and then you insert where you went to, and you increment the counter by 1, right? And every time you go from A to B, after that, you increment the counter again. And that counter is just giving you some kind of confidence, right? Like, have you seen this pattern occur before? And once you keep seeing that pattern and it increases a couple of times, you have some confidence, and you can say, hey, if you're accessing A, go ahead and fetch B, right? And the same thing for if you access B, you fetch C, and so on. You can use this kind of recursively, which is, if you're at A, you can fetch B, and then when you're fetching B, you can go back to the table and go ahead a certain number of nodes. So then you can fetch B. You can look at B and you say, oh, that's C. You can look at C and say that's D, and go to D. And at some point you'll get a thing that it's okay. I don't have enough confidence, so you'll stop there, or you'll exceed your prefetch quota. Like how many nodes ahead you want to walk. Right. So this kind of helps you build out correlation, the temporal correlation, store the temporal correlation, and then exploit it to do these accesses. Now, again, the actual benefit of this thing is dependent on the type of data structure, right? Like, so this seems to work for a linked list. What would it do for a tree? How well would it do for a tree? How would you use this for a tree? Right, so we know what a tree is. Let's draw a tree. And A, B. This is hard, drawing with a mouse. Oh. Right, whatever, you get the point. Just fill out the tree, okay. So how well does this data structure perform for the tree?
You could
Yeah, go for it.
could you make a more complex table, like being able to see all potential like paths that it could take, and then find the counter based off that, and have like a probability for each path?
Could you explain that again? So let's deal with this in a structured manner, right? Like, what is the index into the table that you're describing? What do you index into the table with? What is this operation?
I'm thinking about it for a tree now. I don't know.
Okay, let's go with, it's the current node that you're using, right? And then what were you saying you would store?
The possible paths that it could take, and then it's free.
Okay, let's work that out for A. What do you get for A?
BE.
What's this entry? Okay, so you're saying I'll have A here?
Yeah.
Okay, a B and then a counter?
B and then an index. Yeah, and then E and then an index.
Okay, that's makes sense for a non-linked list tree. In fact, for a general pointer-based data structure, you can use a Markov model, right? Like, you can kind of approximate the transition between elements in the tree as a Markov model, which is really just a closed finite state machine. And the way you would, you'd have a certain number of states available for each node. So each of these nodes can transition, in this case, 3 times, three different directions. So you kind of store whatever, A, B, C for A with the probability of going there. And then you just pick the one with higher probability, right? But then, if you have an n array tree, now you kind of need a correlation table that can store some n entries, right? So this kind of works. It's the most, like, it's a natural structure to build, but it also kind of grows exponentially, because as you're trying to cover more stuff, your entries in the thing, you need n entries for the nodes, and then you need whatever the depth of or the breadth of the tree for entries. So the table works, but kind of, becomes a little too expensive. Can we do better? Can we do something else such that we don't need to grow exponentially?
Yes.
Well played. What can we do? What about so if you had that tree? Oh damn, the tree's gone. All right, fine. Let's just move on to the next slide so I can get the damn tree. I didn't want to draw it. So if I was DFS traversing this tree, right? How? First of all, like everybody's familiar with DFS traversal. Somebody not familiar with that? Okay, I'm going to take that as everybody knows what I'm talking about. Just for argument's sake, you know, the depth first traversal here, you'd go to A, you'd go to B, you'd go to D, then you'd come back to B and go to E, right? And then you'd come back, go back to A, go to C, the F, go back, go to G, and then return to A, right? That's kind of what is encoded out here. So one thing that we can use for you know, keeping track of what to prefetch for something like a tree is to keep track of history, to say what were the two previous nodes that I looked at, right? So if I start at AB, I know that the next node I should go to is D. But if my last nodes are BD, then I know the next node I should go to is B, right? And at B, the last whatever, at that case it's DB, and then you go to E, and BE, and then you go back to B, and so on. So now you can store this kind of tree, this kind of correlation table that encodes history, access history into the table. Now this has much better accuracy because you're using how you traverse as part of this thing, as opposed to the question of if I'm at A, do I go to B or do I go to C? I don't know. Depends on where in that traversal you are, right? The previous kind of predictor would have said go to B, and the first time it's right. But what happens when you've already processed this subtree and you come back up and you want to process this side? It still says go to B because the weights in there are higher for B, whereas for C it's 0. It has never seen C before, or maybe the second time around it has higher weights for B and lower weights for C, and so having a predictor that uses history into its access, into its lookup, right? So it says, instead of looking at where am I right now, it looks up at where was I 1 node ago, 2 nodes ago, and so on. It goes through. Now, how does this structure do in terms of storage? I mean, I know it says exponential storage cost, but can you understand why it's exponential storage cost?
Yes, because there's more possible combinations of things that could be done. So instead of just A, you've got A to B, or B to A, or A to C, C to A, etc. Right.
So you've got more entries in the table. You've got exponential 2 power whatever. If you're storing 2, if you have history of 2, it's 2 power something. If you have history of 3, it's 3 power something, and so on. Yeah. So that's another way of solving the same thing. Now, neither of these are actually going to be really good with storage, but again, everything is a trade-off. And so depending on the kind of workloads you're expecting, the storage may be worth it. In this case, the storage cost for this kind of a table tends to be similar to the pairwise correlation table, but has much greater accuracy. So most of the time, you'll see this kind of a thing implemented. But that said, there's lots of other ways of trimming down the storage needed here, but we're not going to get into that. This is just to give you an idea of what kinds of history tables exist, what kind of patterns exist here, right? So let's look at a different, before I go there, questions up till here. I think we're going to stop looking at pointer-based structures. Well, not quite, but yeah. At least the simpler ones, we're done with that.
So temporally isn't really useful.
Temporal, I mean, both of these are temporal in a sense. I didn't understand the question.
Never mind.
I didn't understand the question. It's like, did I miss something? Like,
So, no. I was just speaking aloud. I didn't realize I was unmuted.
Okay. Right. So, any other questions with this stuff? You can build both things. There's a different way of. There's a better way of encoding temporal storage, which is using some amount of history. There are actually predictors that use this kind of history and then a long instruction stream that's like a circular target buffer kind of thing, and then you index all over the place, so you can share. You can share where you can share the targets, so you don't need to have a single, a repeating stream. Like you don't need to have BB repeating. You can have a circular target buffer, and then the hashing here kind of hashes to both of them hash to the same spot. Well, it's not a hash function or whatever. It's a cuckoo hash function, right? Like you can kind of have the same thing. Yeah, so there's multiple ways that people optimize this stuff, but yeah. Okay, we're moving on to slightly more complex things where you have spatial correlation. So this kind of stuff shows up, where you have database. An example is in a database, right? So it's a completely irregular layout of data. So if you look at a page in memory, the first parts are the page header. So you typically access the page header, then you access the tuple slot index, find the tuples you're interested in, go into those tuples, and then extract the stuff that you're interested in, right? Like so the columns that you're interested in. The layout of these things is highly irregular. So if you can look at the memory snapshot on the side, you can see that the pages that the tuples that we're going to access in each page are all over the place. Like these two are similar. This is something different. This is something different, and so there's no pattern there. You can't also the data is also sparse in that it's not tightly packed together, and you just fetch that type block, and then you don't care which part of the block is accessed. So it's all over a page, and page is if a page is 4 kilobytes typically, and in this case we're assuming it's an 8 kilobyte page, and cache line size is 64 bytes, right? So you have what, 2 power 12 divided by 2 power 7. So you have 5 orders of magnitude difference there, I think. But there's still a pattern here, which is that, you know, the accesses within a page tend to be repetitive. If you're doing a certain computation, you typically access those particular columns times. So, you know, there's the way you kind of build that correlation table, the spatial correlation table. You kind of divide memory into logical regions. And then you'd identify a region by a base address and keep a correlation table where you say, you know, I access load this cache line, load this cache line. You know, don't load this one, load this one, so on, right? For the whole page, you'd say which cache lines are touched, which ones are not touched. And then you'd insert one entry for each of these regions. Now, a region does not need to be a page size. As we saw here, there's actually 2 of these pages that have the same pattern. So then you can kind of store the same pattern for, you know, this and this in one entry, and so on, right? And that's a bit of an engineering decision as to which whether you keep it you know, in one entry or multiple entries. Right, so that's kind of how you would handle, is one simple way of handling within page spatial locality. We're not going to spend much more time on that. So then there's the question, I think somebody asked this, maybe with the branch predictors last week, of, you know, how do you decide when any of this speculative hardware, both branch predictors and prefetchers, are primarily hardware that exists to allow you to prevent stalls in a, you know, in some deep pipeline, right? Like they're essentially there to make sure that we can get some data in, or some the instruction stream in, so that we can keep computing something, even if it's useless, even if it's, you know, the wrong thing and you want to throw it away. But that kind of means that you are now spending some hardware, some space on your chip to do, you know, to gamble. You're trying to say, you're gambling that, hey, I think this will be worth it. You don't know if it's going to be worth it, but you hope so. So there are a couple of things that you need to, you know, that typically people think about when they're implementing a prefetcher. Sorry. One, can I just use the same hardware for a larger cache? Would that help? Right? Like, instead of building all of this complex prefetcher, can I just use a simple prefetcher and a humongous cache, right? Like, just take all of that, well, not a humongous cache, but all the hardware that would be dedicated to the complex prefetcher and put it into a larger cache. Something to, you know, think about. You got, you know, the basic, now that's one, you know, dimension of things that people look at. Other things that people look at is, you know, coverage, accuracy, and timeliness, right? So coverage is how much of the data access, you know, space does your prefetcher cover? So like if you only had like a next line prefetcher, but you had a stride access pattern, your coverage would be really bad. So that would kind of be calculated with prefetched hits divided by base misses, which is all misses. The accuracy is how many of the prefetched things did you were accurate, were, you know, the right thing, right? So that would be kind of prefetch hits by total prefetches. Timeliness, which is the latency of the prefetched block divided by hit latency. So does it make sense for you to even use that particular prefetcher? Some prefetchers are really complex and take a long time. An example of a really, really complicated prefetcher would be there's I think this is early 2000s, and actually is implemented in AMD's Zen architecture. It simulates, it's called Perceptron, and it simulates a neural network, a very simple neural network. But it's, it's proposed in 2000s, kind of only made it to hardware in like middle 2010s, because there's so much work to get it to be timely. It was just so long for it to make a prediction that, they had to work on it to cut that latency down. And then there's, other secondary metrics of things like how much are you polluting the cache, right? Like, are you just fetching stuff that's never going to be used and throwing away useful things that could have been used, right? How much of the total bandwidth are you using? Is the prefetcher out of control? Is bringing in stuff that nobody needs, right? Like if the working set of the piece of code that you're running is actually just limited to some small thing, and then the prefetcher is just running ahead and bringing all sorts of random stuff in, right? Are you wasting bandwidth? Are you wasting power, energy, area? All of these things to think about when evaluating a prefetcher.
So, quick question.
Yes.
I initially thought that after this conversation, I'm seeing why prefetching can also degrade performance, because the cache misses can essentially, you're evicting things from the cache that would have otherwise been there and may have been used, correct? Are there any other points where prefetching can degrade performance?
Bandwidth. You might lock up the memory bus, fetching random garbage that the program doesn't need, and then the program's short enough that it's contending with the prefetcher to bring in data that it needs.
Okay.
Right,
So,
when the prefetcher just cannot predict that pattern.
Okay, and so if I were to turn off prefetching, I'm not even sure if that's possible, but if prefetching was to be turned off, how bad of a performance hit would that be?
You can turn off prefetching. It's typically a BIOS option. It depends on your workload. If you have regularity, if you have your data has some regular pattern, and HPC workloads and things like that, they spend a lot of time tuning their algorithms and their data structures to expose regularity so that they can get this performance bonus, benefit. Turning off the prefetcher when you have regularity can double or triple your time, your execution time. But that, again, it's a very well-tuned program. For an average run-of-the-mill program that has not been tuned and stuff, but has some phases that are regular, right? Like, so a part of your program is regular, a part of it is irregular. Even then, it can have like 10, 15, 20%. And then, of course, you have the programs that are just irregular, and the prefetcher's really introducing maybe a 50%, 60% overhead. And in which case, you turn off the prefetcher.
Can it be turned off per process, or is it the full processor thing?
No, it's a processor level directive. So they tend to turn it off when they're sure that they're running a program that is not going to benefit from a prefetcher. You usually do this with profiling, right? Like, you profile, you look at hardware miss counters, hardware hit counters, hardware prefetch, the accuracy counter for the prefetcher, and then you say, hey, wait, the prefetcher is doing really, really badly, and you turn it off, try again, you'll see a better performance, and then you move on. So yeah, that's kind of how it is. It is processor wide, not process specific. Yeah. So yeah, like actually, I'm just gonna skip this because I don't think it matters for. I'll end with this one, which is, what's inside today's chips. You typically see the data L1 will have a localized stride predictor and a short stride predictor within a block. So it prefetches, the next block kind of thing. The instruction L1 typically tends to have a thing that predicts the future PC. So it's either, at this PC, do I go forward, backward, that kind of thing, right? Like it was like the branch target predictor, similar kind of predictors for that. L2 typically have the next line prefetch and stream buffers. So you want to be able to bring in the next n lines, or bring in the next chunk of data, right? Whatever the thing may be. Later, more recent hardware also kind of the adjacent line prefetcher works across pages. It didn't used to before because you had to do translation. And of course, it only works across a page if you have the entry in the TLB. It doesn't do a page table walk. That'd be too slow. But yeah, I think if you take nothing away from this entire class, this entire lecture, take away that there are prefetchers. Sometimes in very specific situations, they can do bad things. You can turn them off. Most of the time, you'll see a pretty reasonable benefit from them. Just an interesting, challenge. Every year there's or maybe every 2 years, I don't know. There's a prefetcher design championship, right? It's not your prefetcher doesn't need to be synthesizable, right? Like it doesn't need to be realistic hardware. I mean, I guess the challenge kind of has realistic and non-realistic categories. And they usually provide an infrastructure that you design your prefetcher, you write it in, and you can compete. I can post the link to that if people are interested. But yeah, just a fun thing. And with that, we are done with prefetching. We will move on to multi-socket. Do people have questions about? Oh, people are using the chat. Okay, I didn't see that. Yeah, I will post that. So yeah, we're gonna move to multi-core. Before we do, other questions about anything really, prefetching, branch prediction, other stuff till now, something to help you synthesize, where all this stuff fits in, maybe. Okay. So you've seen, I think, most of what a single CPU would be. There's a couple of things that I've left out till now, which is vector computation. Right, and we'll probably cover vector computation later. I've just left that as a separate thing because we'll deal with, we'll finish general CPUs and stuff, and then come to looking at different types of computations and how actually you can build processors that are more suitable to specific types of computations. What are the characteristics that different types of computations exhibit, and how do you take advantage of that? That's been more of a recent trend, recent being maybe the last 5-10 years. So with the rise of GPUs and then now TensorFlow processing units and all that kind of stuff. But yeah, before we get ahead of ourselves, let's look at the transition from single core to multi-core, right? Now, one of the the prime directives for most computer designers, right? Like whether you're a software person, whether you're dealing with software systems or you're building hardware systems, is provide more performance. This is kind of why people buy computers, right? Like scientific computing people, biology people, even now with the AI trend and everything, right? People buy computers to do computation on them, and they expect kind of the new machine that they buy does something better than the previous machine that they bought. So either it's faster, it can handle more complexity, it's cheaper to run, has better battery life. In case of a mobile phone, you buy a new phone, more RAM, better battery life. The better battery life really comes from optimizations in the processor or turning off the processor, etc., right? So let's focus on getting more performance first for a while. When we're looking at getting more performance with processors, for a while the whole way people thought about things was you just kept pushing IPC, and frequency, IPC being instructions per cycle. So as you keep doing that, performance will come. You can keep the ISA the same, and everything will be great, right? And this kind of worked until the mid 2000s. We went from hundreds of kilohertz processors in the 70s and 80s, Hertz processors in the 60s, to several gigahertz, right? Like 2 point something, 3 gigahertz. That's quite an improvement in frequency. But and people predicted that would just keep going. We were supposed to be sitting on machines that run at 20 gigahertz and 30 gigahertz right now, or maybe even terahertz. I don't know. It's been 10 years since that prediction. But that has not kept up. I mean, none of us has even heard of a machine that can run at 10 gigahertz, right? There was one, but that was a different story. Why? What happened? Does anyone want to take a guess?
Limitations of the physical properties of the chips.
I can't hear you. You're too far away from your mic.
There were like limitations to the physical properties of the chips, like their like the elements themselves.
Well,
like with thermal stuff.
No. So, yes, there are physical property limits, but we're not talking about, this is the mid 2000s, so we're not talking about physical property limits yet. We're still, from 2000 something, 2005, 2006 till I think 2 years ago, we were still scaling transistors. More than that, there was, I think you kind of mentioned it with the thermal thing. It was more that the rate of growth of power consumption did not kind of keep, like, you were not able to keep shrinking transistors and then be able to design a much more complex, and the reason why we care about shrinking transistors is for the same area we will be able to design a more complex processor in that area. And the area matters because the production the larger your chip, the more likely it is to have errors, the more likely it is to have faults, right? Like during the production, you'll have manufacturing problems. And so if your chip is small, then the problems are kind of localized to certain numbers of chips. So you can throw those away and then, you have some yield rate of whatever, right? Like if one ring, one disk kind of has 100 chips, and there's, you have an error rate of 3, you can throw away 3 chips and that's fine. If your entire chip is that big, then, you have a problem. Now, that scaling kept happening until about 2005, somewhere around then, when people started realizing that you could still kind of pack more transistors into a smaller chip, but now the power that it took to power the entire chip was not staying constant. It was actually spiking. We'll see that in a second. So if this graph kind of shows that we went from single issue pipelined to superscalar out of order, and you have this nice, it's a log scale, so you have this nice linear growth, and then it kind of went from there to if you could go into this really hypothetical, aggressive superscalar out of order machine that we could build in the future, we could actually it actually kind of tapers off the performance that you can get from that. And the reason is that the power has been growing exponentially. And so by the time you get to this, you're not keeping up, one, and this power is going to become a problem because the chip may melt. Now you need to spend more money cooling more power to cool the chip to take away the heat that is generated. And another way of putting this, if we were to draw effort on this scale with the different types and performance on another scale, we actually kind of found that up till this point we had good return on investment. We got a good, reasonable performance bump for effort. But then hereafter, we started seeing a really, really minimal gain in performance for a massive increase in effort, right? And so this kind of gave way to an alternate way. Like, people started thinking about the problem in a different way, which was, until then, all performance gains had been free to the programmer, right? By free, I mean if you wrote one piece of software and you deployed it in, say, 95, and then you bought a new chip, a new machine in 99, and you ran the same piece of software, no recompilation, no rewriting, no anything, and you ran it on the new machine, you typically, the program actually typically ran faster. A very interesting example of this is, I don't know, how many of you have played Doom, not Doom, the 1990 game, not the new one.
Yeah.
Okay, some people would have. So this game was written in the early 90s for Windows 3.5 or whatever, 95, something like that. And when so I think it was written for 3.5 and then they ported it to 95, the processors had improved so much that the game was unplayable because the way they had written the main loop kind of assumed a certain frequency of instruction processing. They'd written their code in, specifically for that, for the machine that they had at that point, essentially. And then as you tried to run it on a newer processor, your game was running 3x faster, 4x faster, like visually 3x faster. Like you were literally running through the room, 3 times as fast. Everything was operating 3 times as fast. Just a funny aside. But so yeah, I mean, that was bad programming, right? Like you shouldn't tie your program to running at a particular frequency. But yes, that's just another way of illustrating that till then you were getting speed ups by just buying new hardware. And the way the way this also operated was you had the same ISA. You just kept changing the microarchitecture. So the interface, the ISA stayed stable. Underneath, you did whatever you wanted, right? Like what we've looked at the entire class till now. But that was no longer possible, and so we looked at a new way of dealing with these things, which is there is parallelism in programs. So either there's unrelated computations that could both run at the same time, or you're running multiple programs at the same time in a computer. Till this point, you were essentially time multiplexing, your music player, your browser, and something else. But with you could exploit that by saying, hey, I have more transistors, but I can't put them to I can't pack one entire design across the whole thing because there's going to be a lot of problems with transferring data and all of that. What if I were to stamp 2 of the same processor twice, right? Like I've some area, I put 2 processors. Now I can run 2 things in parallel, just a more coarse-grained parallelism. Instead of instruction streams, I'm now running like 2 different processes or whatever. The change here, the big change here, is that prior to this, most parallelism was found by the microarchitecture. The microarchitecture was responsible for looking at an instruction stream and saying, hey, I see an opportunity there to speculatively execute something, to run ahead and do those things. Whereas with exposing 2 different processors, now you're asking the developers, hey, you need to find parallelism. So yeah, that was one way of looking at this, which is is this user visible or user invisible change? So the move to multi-core is a fairly user visible change. Yeah, as we were saying, it makes sense because you're either running different applications or you have multiple threads within one application that are doing different things. So this kind of also gave rise to the whole p-threads, the thread library standardization, and MPI and OpenMP and all of that kind of stuff. So the first way of building this kind of a machine, right? Like if you wanted to run multiple processes at the same time, was this had existed for a while before we moved to multi-core. Was to build a CPU, a computer that had multiple physical processors in it, right? So this is typically called symmetric multiprocessing, where symmetric because all CPUs have equal access to memory. So if you see there's these 4 memory channels here, and all these 4 CPUs essentially have equal access, typically through another controller here, this metal thing. You guys can see the mouse, right?
Yes.
Okay.
Yes.
Thank you. So you typically had equal access, and the way the OS managed this, of course, is that you saw 4 CPUs and you had 4 scheduler queues, and you ran things that way. So multiprocessor kind of is, if you have one really good CPU, you take 4 of them, and now you should be able to do a piece of work 4 times as fast, right? So if you had like a 3 wide out of order CPU and it took this much time to run 2 tasks, right? So because you have 1 CPU, if you go into a bigger CPU, a 4-wide out-of-order CPU, same core, just one more lane, would give you, some benefit, right? But if you went, double, you could run task. You had 2 of those 3-wide out-of-order CPUs instead of 4-wide. You'd have, much more benefit because you could execute task A and B in parallel. Now, you could also argue that, why not go one level down in the complexity of the CPU? So why not have a simpler CPU? Each task takes a little longer, but you still have some amount of benefit, right? Because you're still actually doing better than having one large CPU. And maybe you can actually implement these 2 in the same area that the 4-wide takes. Well, it's a reasonable question to ask. Anyone see a problem with this? Okay, there's an assumption, which is that you have multiple tasks or programs to run. What happens when you have only one process, right? When you have a 3-wide CPU, it takes that much. 4-wide, a little better. You have 2 of these, no real benefit, that's fine. You come to the 2-wide, you actually have a performance degradation. So, the question then becomes like, I'm not saying that, using a less dense CPU is always a bad idea, but there is that trade-off where, you may do so for energy reasons. You may do so for, like, your mobile phone CPU is, less, they're still quite complex, but they're less performant than a Xeon that you would see in a server, right? So that would kind of be the trade-off there.
What does the OOO stand for again?
Out of order.
Out of order, okay. And if there's only one task, why is the 4-wide? When you say 4-wide, you mean 4-core?
Oh, no. So this is a superscalar CPU.
Okay, never
This
mind.
is still a single core. So the 4-wide is 4-way superscalar.
Okay.
4-wide superscalar. Yeah. And the other thing is, of course, that the benefit of having multiple processors is also, it does also depend on the workload itself, right? Like, so this is Amdahl's law. You guys remember Amdahl's law from the first lecture? It's essentially states that, the maximum speed up that you can gain from parallelism is dependent on the percentage of your task that is parallelizable, right? So if you had this task that, the pink stuff is not parallelizable and the green thing here is parallelizable, throwing more CPUs at it will make the time taken to run this thing much slower, but do nothing for the first part, the pink part. So it requires, usually requires adding more processors, requires people to rethink the way they write code, right? Which is, you cannot think of, you cannot design algorithms that, only that are completely dependent on previous execution state and things like that. So this has kind of been the big challenge for the last 15 years, sort of, as to how you would design, how do you design better programming languages that allow you to express parallelism? How do you design better algorithms that are parallelizable, and so on? But that said, this is kind of the direction that we've gone in till recently. I mean, we're still going in that direction, so we'll see more about it. What else? What do you have to change for a symmetric multiprocessor system? right? Like physically, what do you have to change? Couple of things will, obviously need to happen. The motherboard will need multiple sockets. Till if you have only one socket, you can't use the other one. And you need some way of maybe connecting the different CPUs up. Your processor itself will need to have a different memory interface so that it knows that it's not the only one accessing that memory. So maybe it has to go through an indirect access to the memory, right? So we saw that there was another chip that had to deal with that. So the memory interface changes. The motherboard, multiple sockets. You need to have more data paths between the CPU and memory, or CPU and the controller, and so on. And then the more you need more cooling, more power supply, more maybe a larger machine, the case, bigger motherboards, better airflow, all of that kind of stuff. So changing, it's not like there's more overhead to that. But so then, people started exploring the idea of, well, can I reduce a lot of that overhead by having more processors on the same chip, so that I can keep the same old way, the old stuff where I have like one lane between memory and the CPU, only one socket, less cooling, it's a smaller box, all of that kind of stuff. But put more of the processing elements on a single chip, right? So CPUs are now multi-core. They have been for, I don't know, 10 years or more, maybe 15 years. And the idea is essentially that it's to take, what would have been two separate chips and put them into one die as you have shrinking transistors. So yeah, here's a block diagram for one of these. You have one chip here, one core here. They're really just identical, and they have their own L2 caches and controllers and all of that, and then they share a common system bus, and they talk to the rest of the memory and other devices and all of that, over a common bus, right? Similar on this is the AMD Athlon, pretty old. It's a dual core machine. The two cores are shown here. This is kind of the system bus interconnect thing and some other stuff. These are the two cores, caches. You can see more caches here. And I guess this is the shared caches between the two cores. So CMP introduces a bunch of new things, right? Like you have networks on the chip to connect between the two cores and all of that. I'm actually going to stop here because we have like 5 minutes left, and allow you to ask questions and talk about history of computing. Yeah. So yeah, questions on, I don't know, anything really, the computing, multiprocessors, multi-core, why things are the way they are.
When did it become apparent that multiprocessing would be necessary?
So SMPs have been around since 80s, 90s. So that that has been around forever. IBM would sell mainframes that had multiple processing units back in the 60s. So that kind of stuff has existed forever. More PC-based things coming, embracing multi-core is kind of the 90s with SMP. So you'd have multiple chips. moving into the chip multiprocessor era is, I would say, mid 2000s. Yeah, the dual cores started popping up in the latter half of the 2000s, and then you start seeing more and more and more cores in the 2010s. And then you're actually seeing other things being put into processors in the later 2010s, or the mid to later 2010s.
Is the number of cores, like, is there Moore's law for the number of cores as well?
There isn't. So I think the reason that happens is that at some point, adding more cores to your chip may not be useful. There's a couple of different trade-offs. One is that as chips get smaller, somewhere in the mid 2010s, we realized that we can't actually power most of the chips. So you can build a processor that has 16 cores and 2 threads of core, so you have 32 threads of execution. But we've also found that we can't run all 32 threads at the highest frequency. We have to limit the power consumption for each core down to run it at half of its top frequency, so that you can actually run the processor without specialized cooling infrastructure. So water cooling or whatever. So if you're just using air cooling, we've actually had that problem. So there isn't a Moore's law. In fact, we're going in a different direction with most machines today. Your iPhones and your whatever, right? Like whichever phone you use, your processor has a set number of CPU cores, some GPU cores, and then a seriously large amount of other accelerator cores. Let me see if I have a picture of that. Yeah. Change the sharing here. Right, so this picture. You guys can see this, right? This is the chip that's in the latest iPhone, and the CPU cores are here. The big core is a slightly more complex core, and the little cores are more wimpier cores, but more of them. So there's 4 of them, and there's 2 of these. There's some GPUs on this side. There's a neural network engine here. They're really just, both the GPU and the neural engine are really just regular processing cores with a very different, they're optimized for a very different type of computation, right? So the way they access memory, the complexity of each execution unit, the kinds of execution units on the thing, all of these are where changes occur. And then these little boxes that you see all over the place, right? So there's DDR logic in those 2 places. There's probably some other kind of communication control everywhere else. But all the other stuff that is labeled here in boxes there's some kind of accelerator. There's some kind of computation core specialized for other purposes. So some of them will be like the wireless, so there'll be DSPs that are dealing with radio signals. There'll be your camera cores.
Computing hashes.
Computing hashes, computing encryption, computing camera, so dealing with the output of your camera, right? Yeah, you get some signal, you want to apply filters on that, you want to do whatever. There'll be processors for that. So we've gone in that direction where a lot of this chip is dedicated to single tasks. Now, the only way that works is most of this chip is dark most of the time. So it's not doing anything most of the time. I mean, like the units, each individual unit is not powered all the time. But when there's an application that wants that task, you power that one on, you use it, and then you power it off. So that's kind of how we've gone with dealing with the issues that have arisen. All right, that was I hope that was enlightening. And with that, we are done. It's 3:15. I will stop the